A radar system sends out energy. That energy hits an object and bounces back. The radar measures what returns. That's the entire principle, and it has worked reliably since the 1930s. Stealth doesn't break that principle. It doesn't jam the radar. It doesn't bend physics. It does something more precise. It controls what bounces back and where it goes. The radar still works. It just stops receiving a useful answer. Every air defense system in the world is built on radar. Surface-to-air missile batteries, fighter intercept queues, airborne early warning aircraft. All of it begins with a radar return. Reduce that return below the level needed for reliable tracking, and the radar-based portion of the kill chain begins to break down before it starts. China and Russia have invested heavily in long-range, high-powered radar networks, specifically designed to detect low-observable aircraft at range. The S-400, the HQ-9, VHF early warning systems. These are not legacy threats. They are current, fielded, and oriented toward defeating U.S. stealth. Understanding exactly how stealth works and where its limits are is the only way to evaluate how that competition is actually going. What radar cross-section actually measures. Radar cross-section, ORCS, is not the physical size of the aircraft. It is the measure of how much radar energy an object reflects back toward the receiver. A large aircraft with carefully shaped surfaces can have a lower RCs than a small aircraft with flat panels and right-angle joints. ORCS is measured in square meters, but the number does not describe area. It describes reflective behavior. A Boeing 747 has an RCs of roughly 100 square meters. A conventional fourth-generation fighter, an F-15, a Su-27, is typically assessed in the range of several square meters, depending on aspect. The F-22's exact RCs is classified, but open-source estimates place its frontal radar cross-section several orders of magnitude, smaller than conventional fighters. The F-35 is assessed similarly from the front quarter. That difference is not cosmetic. Radar detection range scales with the fourth root of RCs. Reduce RCs by a large enough factor, and detection range drops dramatically. A radar that could detect a conventional fighter at long range might only detect a stealth aircraft at a fraction of that distance. The geometry of the entire engagement shifts. Shaping, the primary tool. The most important stealth technique is not coding or material. It is geometry. Radar energy reflects strongest at perpendicular surfaces. Flat panels hit straight on. Right-angled joints where two surfaces meet. Inlet edges, canopy frames. A conventional aircraft is full of these. Many of these features behave like radar reflectors, sending energy back toward the source. Stealth shaping eliminates perpendicular returns by ensuring that every surface redirects reflected energy into specific directions, away from the radar, rather than back toward it. The F-22's fuselage is composed of carefully angled facets. The leading and trailing edges of the wings and tail surfaces are aligned to the same set of angles, a technique called edge alignment. This concentrates any reflected energy into a small number of specific directions, called spike angles. A radar that is not positioned at exactly one of those spike angles receives almost nothing. The inlets, one of the hardest problems in stealth design, hide the engine face behind curved S-duct inlet passages that prevent a direct line of sight to the compressor blades, which are powerful radar reflectors. Weapons are carried internally. External pylons, fuel tanks, and weapons create their own radar returns. Internal carriage eliminates them entirely. This is the key insight. Stealth aircraft are not invisible in all directions. They are invisible in most directions, most of the time, because the threat radar is almost never positioned at one of the spike angles. Managing geometry means managing probability. Radar absorbent materials, the second layer. Shaping handles the structural returns. Radar absorbent materials, RAM, handle the residual. RAM works by converting some of the radar energy into heat and reducing the strength of the reflected signal through a combination of dielectric absorption, magnetic loss, and destructive interference. It is applied to leading edges, inlets, and other surfaces where shaping alone cannot eliminate the return. RAM has limits. It is frequency dependent. Materials optimized to absorb X-band fire control radar frequencies perform differently against L-band or VEET early warning radar. Stealth coatings require maintenance to preserve performance, though modern materials are significantly more durable than early stealth coatings. Operational availability is still a real sustainment consideration, but less acute than in first-generation stealth programs. Emissions control. The third layer. An aircraft that shapes its structure and coats its surfaces can still be detected if it is broadcasting. Radar emissions, radio transmissions, data link signals, all of these are detectable by passive sensors. A stealth aircraft operating with its radar in full active search mode is radiating energy that a threat-alert system can locate and potentially track, regardless of how low its structural RCs is. This is why emissions control is part of stealth doctrine, not just stealth design. The F-22's AN/APG-77 uses low probability of intercept modes, frequency hopping, spread spectrum, modulated pulses, to reduce the detectability of its own radar emissions. Data link usage is managed. Radio discipline matters. The aircraft's physical stealth and its electromagnetic discipline have to work together. One without the other creates a detectable signature. Baltic region. An S-400 battery is operational, covering a contested corridor. Its engagement radar operates in X-band, high-resolution, fire control quality. Its supporting early warning radar operates in a lower frequency band, optimized for long-range search. A flight of F-22s enters the corridor at altitude. The S-400's early warning radar is searching. Against a conventional fighter, it would have a detection range sufficient to cue the engagement radar and begin the intercept sequence with time to spare. Against the F-22, the geometry changes. The detection range compresses. By the time the early warning radar gets a return strong enough to classify and track, the F-22 element is already inside the window, where the battery must react quickly to generate a firing solution, and the pilots know the radar's position from R-94 passive detection, which identified the S-400's emissions well before any radar contact was established. The engagement radar attempts to lock. The F-22's reduced RCs means the lock is intermittent. The radar is working at the edge of its sensitivity. The fire control solution is degraded. A weapon fired on an intermittent track has a materially lower probability of intercept than one fired on a firm track. The F-22s release standoff weapons and turn cold before the S-400 can generate a valid firing solution. The battery never achieved the continuous track it needed. Stealth did not make the aircraft invisible. It denied the radar the time and data quality required to act. Stealth is not a permanent condition. It is an advantage that degrades under specific circumstances. Vichvendoff radar, lower frequency bands, interact with stealth geometry differently than X-band fire control radar. At lower frequencies, the wavelength becomes comparable to the aircraft's overall dimensions, creating resonance effects that increase detectability. Russia's Nebo-M radar system and China's Ji-26 operate in these bands and are assessed to have some detection capability against low-observable aircraft. Detection, however, is not the same as tracking with fire control quality, and a track that cannot support a weapons solution does not close a kill chain. Bistatic and multistatic radar, configurations where the transmitter and receiver are separated, remove one of stealth shaping's core assumptions. Stealth geometry is optimized to deflect energy away from the transmitting radar. A receiver positioned at a different angle may be sitting exactly where the deflected energy is going. This is a known vulnerability. It requires significant infrastructure to exploit at scale, but the concept is sound, and adversaries are investing in it. And an aircraft that is stealthy at long range becomes increasingly detectable as range closes, not because stealth fails, but because radar sensitivity is a function of range. Close enough, and almost anything can be detected. Stealth redefined what air power can do in a denied environment. Before low-observable aircraft, penetrating a modern integrated air defense system required either standoff range, overwhelming electronic jamming, or acceptance of significant attrition. The F-117 demonstrated in 1991 that a small number of stealth aircraft could strike targets that would have required large conventional packages at high cost. The F-22 and F-35 extended that logic to air superiority and multi-role operations, respectively. The adversary response has been layered and specific. Investment in VATF early warning radar to complicate detection geometry. Investment in bistatic receiving networks to exploit stealth's angular vulnerabilities. Investment in passive burst sensors on fighter aircraft to detect heat signatures that stealth shaping does not significantly reduce. Investment in longer-range surface-to-air missiles that push the engagement envelope outward, reducing the time compression that stealth geometry creates. None of these individually defeat stealth. Together, they complicate the operational calculus. A stealth aircraft entering a layered threat environment faces a system specifically designed around its vulnerabilities, each layer covering what the others miss. The U.S. response is not to abandon stealth, but to layer it differently. The B-21 Raider applies a new generation of shaping and materials. NOD will extend the low-observable architecture into the 6th-generation fighter. The broader shift is toward distributed operations, where no single platform carries the entire penetration burden, and where the detection problem is complicated not just by one aircraft's arcs, but by many aircraft operating in coordinated electromagnetic silence across a wide area. The underlying physics haven't changed. The scale at which they must be applied has. Stealth doesn't hide an aircraft. It forces every radar pointed at it to make a harder decision, with worse data, in less time, against a target that already knows where it is. That asymmetry is the weapon, and it works until the adversary builds a system specifically designed to close it.